Good day, everybody, and welcome to our third OptiSPICE webinar. My name is Brian Tipper. I'm the VP of Sales and Marketing here at OptiWave, and I'll be sitting alongside your host, Jem Bonfil. The webinar today will focus on the advanced features of OptiSPICE. As usual, I'll be launching 3 polls, such as the one you're looking at now, during the course of the presentation. And if you're in attendance for all 3 polls, you'll be entered into our $50 gift card draw. You can find out the winner of the draw on our website in 1 hour. We'll also have 2 question and answer periods, the first one about 15 minutes in and the second at the very end. And lastly, the webinar will be recorded and distributed to everybody that is registered. You'll receive the video link in an email tomorrow. So without further ado, let's welcome your presenter, Product Manager of Optoelectronics, Jem Bonfil.
Hey Brian, thank you for the introduction. So today I'm going to be talking about scripting and post-processing features of OptiSPICE. But before I get to that, I'd just like to go over some background information of OptiSPICE for those who have missed our previous presentations. Our OptiSPICE is based on well-known Berkeley SPICE. Berkeley SPICE, it's a tool that is commonly used. It's the industry standard for simulating analog electronics. In our OptiSPICE, we have actually augmented this by adding optical capabilities to it. The way SPICE works is it takes compact models describing different devices. It could be resistor, capacitor, inductor. It could be nonlinear devices like BJT, MOSFET for electrical models, or it could be optical devices. And OptiSPICE puts all these equations and how these devices relate to each other into one big matrix and then solve it all at once at every time step. You can also do frequency domain simulations with SPICE, and then it would only solve one frequency point at a time, and then you can get your solution. So optical signals are modeled in a certain way in OptiSPICE to make sure that the simulation runs fast. The optical signal is modeled as a magnitude and a phase, or in Cartesian, real and imaginary number. It has a particular mode and a particular frequency. It can be bidirectional, so we have 2 different signals for bidirectional propagation, and the signals can also have polarization. The way we're simulating the optical signal is actually the magnitude, the amplitude of the envelope of the carrier signal and the phase of the carrier signal. If we wanted to simulate the full carrier signal, then we would have to go to very small time steps, which would slow down the simulation significantly, because the carrier signal is in terahertz, where we're mostly interested in the electrical bandwidth, which is in tens of gigahertz range. We have a multitude of optical components in OptiSPICE. We have splitters, optical splitters, joiners, and nonlinear components like laser, optical fiber. We also have photodiodes, so on the receiver side, and you can put these components together to create your electro-optical system. Now, I would like to just briefly talk about the strengths of OptiSPICE. Because of the system matrix approach I described earlier, it is very natural for OptiSPICE to handle any reflections in your simulation or any feedback circuits if you want to do control circuits. One good example would be is if you have a laser and near this laser you have a ring resonator, which the resonance is dependent on temperature. On top of that, you can have a system where you have a detector and a controller which changes the temperature of the ring resonator to change its resonance. So it can detect whether the ring resonator is on or off resonance and then change it, keep it there or change it based on the user request. So imagine when you have the laser, obviously the laser is going to warm up and then it will affect the operation of the ring resonator. And then we can also model the controller that makes sure that the ring resonator operates correctly. So we can model these kind of systems in OptiSPICE. One other strength of OptiSPICE is full optical link simulations, including electrical circuits, such as a laser driver In a laser driver, you would typically have a series of transistors, and then you would use the laser driver to drive the laser directly. And then this generates your optical signal. You can push that through the cable, and then on the other side, you can simulate the detection with the photodiode, and then an electrical circuit afterwards with various amplifiers, and one of the most common one is a transimpedance amplifier. Again, this would have electrical components. And you can also simulate parasitic effects due to the electrical components. For example, if you have flip chip bonding, then you would have some parasitics coming from the connection between the two chips, and you can simulate that. Well, I guess, as I said earlier, we could do multiple domain simulations. We could do thermal, optical, electrical simulations at the same time, thermal being simulated as an RC circuit. Finally, we're working towards, in OptiSPICE, you can simulate photonic integrated circuits, and we're working towards being able to bring PDKs, photonic design kits, into OptiSPICE such that you can interact with a circuit layout tool and a circuit schematic tool and iterate between the layout and the schematic and optimize your circuit. Now let's start with the scripting and post-processing. We have different ways of doing the scripting. One is using the simulation engine itself. You can actually set different parameters and then do some basic calculations using those parameters and then feed them into the models. We're going to show an example in a minute. We can also do standalone simulations with OptiSPICE. What I mean by standalone is our simulation engine is completely separate from our user interface. What the user interface does is it generates a netlist which includes all the information necessary to run the simulation. This information is practically the type of simulation we want to do, the type of models we want to use, the connections all the elements have between each other, and of course the output we would like to have. So if you have a netlist, you don't actually necessarily need, if you know how to create a netlist, you don't necessarily need to use our interface. This helps us interface between different scripting tools. You can any scripting tool that can execute a system command can be used with SPICE. For example, you can use Python, MATLAB, Octave, and specifically with Python, we have actually wrote a library which allows you to load the results from OptiSPICE into Python very easily and then use it for post-processing. Finally, you can do, in OptiSPICE, you can do nested parameter sweeps. That may also enable you to look at optimization of a particular design. So we have 4 examples today. Starting with a ring resonator, I'm going to show you how to basically use our scripting to change the radius of the ring such that we get the resonance at a frequency we want. And I'm also going to show you, actually, with this example, how you can build a ring demux and how 2 channels for this ring demux can interact with each other. So the channel crosstalk. Then we'll talk about the transmission line and how we can calculate the transmission line parameters like loss and velocity of the transmission using Python. And then I'm also going to show you a curve fitting algorithm I developed for our traveling wave modulator, which fits measured parameters into the into the transmission line model that is included with the traveling wave modulator. Finally, I'm going to talk about a Nanophotonic Imager and how we use Python to post-process the results. Okay. We have a basic ring resonator demux here. The first simulation I'm going to show is right here, where you have 2 ring resonators. And here, actually, with the SPICE command, you can create your parameters using the command called .param. Here I define pi, effective index, and lambda 1 is the resonant frequency of the first ring resonator, and lambda 2 is the resonant frequency of the second resonator. And this C-val is the coupling coefficient inside of the cross-coupler inside this ring resonator, and the R is actually the radius. So I'm just using a basic formula to calculate the radius of the ring resonator based on the wavelength I'm interested in. And in the second example here, we have a transient simulation, which is going to show what happens when our channels are too close to each other versus when our channels are far from each other. So here we have basic results where you can see two channels. Maybe I should, if I zoom in, one is at 1550, the other is at 1553. So these channels are far apart. So if we send a signal at these frequencies, then you can see on the output there's not much crosstalk between these two channels. Here we have two channels that are much closer to each other. Now you can see how the channels are affecting each other as a result. Let me quickly show you how this looks like in OptiSPICE schematic. So the first one, the way you can enter parameters is if you double click on the background, which is going to give you the setup menu, and then you go to the SPICE command. SPICE command has all the commands, can accept all the commands you want to put in. It can actually do more than accepting parameters, but here for this example, this is the only feature we're using. Like you can see, I have set up lambda 1, and I'm doing I'm calculating this radius based on this wavelength. And you can actually use this radius parameter in this in this ring resonator model. Here you can see I'm using the radius one, and here this is the coupling coefficient. And this one has a different model with radius 2. Let's quickly run the simulation. You can see they're far apart. And I can change, now I'm going to change the frequency, the resonant frequency, to something much closer to 1550. And you can see how the channels are now interacting with each other. Now let's move on to our next example, this transmission line. Here we're using SPICE, and we're mimicking basic experimental setup to calculate the S parameters for a transmission line. This is a basic 2-port transmission line. And the way it works is it sectionalizes the transmission line into many different bits, and then every piece has its own resistance, capacitance, inductance, and conductance. By changing these parameters, you can change the way the transmission line is behaving. And I'm going to show you now how to set up a script for this transmission line such that we can calculate the S parameter. Now, the way you do it is, of course, first you start with your design, and then you decide the output you're interested in. And then you need to set up two things first. First one is, let's go to the example and start looking at it. The first one is locating where the Python engine is, In my case, it's under C, Python 36. The second is you need to specify the path of the Python script. In our case, it's in the same folder as where I'm doing the simulation. It's the S-parameter script. Now, before we go further deep into how to run this script, I would like to also talk about different file formats or different files we generate when we run SPICE simulation. Let's run the simulation briefly and look at different extensions and different files we get in OptiSPICE. One moment, please. Sorry there, I have just misplaced my documents. Let me go back to desktop and grab the correct document. There we go. Okay. Now, the first one I would like to talk about is the 2D DAT file. This DAT file has actually all the results that the OptiSPICE engine generates. And every column, the first column corresponds to either frequency or time, and the other columns correspond to the output from the probes. Now, there's one thing we're missing here is obviously we don't know which column corresponds to which probe. The way to figure that out is actually to look at this orx.gz file. It's a GNU zip file that you can unzip. Then you can inspect using a text editor. We're going to use Notepad here. It's an actually XML file that once we format, we're going to be able to see what it does. So this XML file includes all the information necessary to understand the output. See, the first, it starts from 0, which means that the first column, it's not the first column because the first column was either the time or the frequency. So this 0 actually corresponds to the first column right after the time or the frequency. And you can see this is signal 1.2 at port is -1 because it's a voltage. It's a connection between the two signals, between the two ports. And we can look at the phase, and we can see what different signals correspond to, and which column each signal corresponds to. We have our netlist here, where it has the information of all the connections, which type of devices we're using, and which monitors we have. It also has the information of the type of simulation we're doing. The next one is the .include file. .include file is an extension of the netlist, and it has the models, but you can actually add any component into this .include file. Now let's go back to our script. Let's run this simulation. And you can click on Launch Python. This is going to launch the Python script I wrote. which shows you the transmission line, different transmission line parameters. It shows you the attenuation, S21, characteristic impedance, effective microwave index. And I'm just going to briefly talk about the script itself. If you look at the script, there are a few things you need to pay attention to. We have, like I said, we have a Python library which helps you get the signals from the output and process them. The first thing you need to do is you need to get the XML file name. You can do that directly by grabbing the system argument that is coming from OptiSPICE, which will give you the XML file name. That is the orx.gz file that we were looking at before. And then once you have that, Python is going to load all the signals necessary, and then you can grab the data you want. See, over here I'm looking at signal 1, 2. It's a voltage, and I want the signal in time domain. You can also get your signals in frequency domain. This Python script is going to do the conversion for you. And then afterwards, the rest is pretty straightforward. You write how the kind of script you're interested in. You can use different libraries for visualizing, and you can do your post-processing. Now we're going to take a break and do a poll, and then I will take a few questions and continue with our presentation.
Okay, thanks, Jim. We're going to go ahead and launch the second poll here. So please feel free to ask any questions you guys have. This is the perfect opportunity for you to make use of basically a one-on-one with our OptiSPICE expert. He's here to answer anything you guys would like to ask, and also if there's a specific application that you're trying to get accomplished with OptiSPICE, please let us know. Feel free to basically write anything you want into the questions panel, even if you'd like a quotation, or you're interested in an evaluation, or perhaps you'd really like us to visit your university and do a training seminar or a demonstration for your class or whatnot. Basically let us know. We're here taking as many ideas as we can to determine basically our steps forward with our different products. So yeah, everything's appreciated. Okay, I'm going to go ahead and close the poll and pass it back to Jem.
Okay, so let's continue with our presentation. Now I'm going to actually show you something a bit more sophisticated than the previous example. Now what this example shows is we have a measured data for an S parameter for a transmission line. And we're going to be using SPICE to find the transmission line parameters for this data, and then we can use this data to run our traveling wave modulator. There are a few pieces in this example. Of course, we need our Python script file. We have a bat file that runs OptiSPICE for the from the command line. I have generated a netlist template where the Python script actually can go and change the parameters in the netlist. And of course, we have our measured S parameter data. And this shows just the basic fit I did for the measured S parameter data. Basically, the way it works is initially you just, instead of launching SPICE from the user interface, you can launch SPICE from Python. So you start your Python script, and we're going to do this to the command line. The Python script modifies the parameters that we're looking for in the netlist. It runs OptiSPICE simulation and then compares the results of the simulation with our measured data. If our measured data and our results match well enough, then we're done with our simulation and with our search, and we can quit. If it doesn't, then we need to go back and get Python to modify the parameters in the netlist and try different values and run OptiSPICE again. this loop will continue until we're able to do a good fit, and then it will quit. Or if we cannot find the results, obviously there is also a limited number of tries it will do. So we don't run our script forever. Now let me go and show you different files that I'm using for this. Okay, the most basic one is running OptiSPICE through the command line. I just wrote a small bat file here, where when you double click or when you run it, it will actually call OptiSPICE. This is where my executable is located. This X ensures that the XML that has the column data is generated. This Q command is actually so that we don't fill the terminal output with too much data. And then the SP file is given as a parameter, so this is the actually netlist we would like to simulate. Now let me go to the template. Here I'm changing the model parameters for the transmission line, and I have named them specifically such that from the Python script we can find these parameters and then give them a value, and then try different values until we're happy with the fit. I'm going to show you the function we use to optimize this Python, get the values for the resistance, capacitance, and inductance. Basically, this function takes in a guess, and then it runs. It first modifies the parameters in the model by looking at the .include file, and then replaces them, and then writes them back. Later, we're calling a sub-process, and we're running the script that runs OptiSPICE. And once we run OptiSPICE, then we can use our built-in library to grab the data. And then, as you can see, I'm getting the electrical signal here. And then compare this data with our results. And compare the results with our measured data and decide if we want to run the simulation or not. We can also plot the results meanwhile we're running the simulation. Finally, the script that controls all this is actually this one, where this is our starting guess, and we're using a Python function called fmin, which will try different numbers for the guess, and then we have our function outputs whether our guess is good or not, and then we iterate over. Let me pull up the command line. The first thing I need to do is to navigate to this location. Now I'm going to run this script by calling Python, and then I'm going to give the name of the script, OptiSPICE optimization. Now you're going to see that the optimizer is going to run a few times, and it's going to try different values. The different values are going to be printed over here. This is the first try. This is another try. You can see every time. So before the resistance was 4.686. Now it's a different value. So it's going to try a bunch of values. Here, just for demonstration purposes, I chose initial values that are close to the final result. However, you don't have to start from such close values to get a good fit. Now, once the algorithm is happy with the fit, it is going to stop. Okay, there we go. We have our final results. Now let's move on to our final example. Here, this is a nanophotonic imager. The way it works is we split the incoming signal into various branches, and then this signal travels in different paths. Let's say we're trying to look at an image at a certain distance, and we would like to measure, and it has certain depth. It's a 3D image, and we would like to measure different depths at different locations. So once we split the signal into many different paths, then we can shine the light onto the image and then look at the reflection. Each reflection from different point of the image is going to travel a different path and interfere with the incoming signal and give a different results. And the way we can measure the distance is actually by first chirping the laser. We introduce a linear chirp, and then this linear chirp interferes with the reflected image and produces a constant difference between two frequencies. And this frequency can then be captured, and by looking at the frequency of the result, we can tell how far the light has traveled. Now let's look at the example in OptiSPICE. Now the first subcircuit here actually splits the signal into multiple channels or multiple points. And then on the other side, we have our receiver circuit with two different path lengths that simulates the path light has taken, the difference in the path taken. And then the signals recombine at the photodiode. So as each signal is going to be traveling a different distance, the difference between the chirp signals are going to result in different frequencies. Then by looking at the frequency, we can tell how far the light has traveled. For this one, I'm actually not going to run the simulation. I'm just going to basically show you the result. Here you can see different frequencies for different receivers. This is our input image, and this is the image that we have received. Each color corresponds to a different depth, and this is all the pixels we have. So we have 16 pixels, and we can see the difference between the actual and the measured pixel. This is so we're measuring about 100 microns over half a meter, so this is not too bad. And I have used again Python to do all the processing. So all we have received from this simulation is actually different frequencies at different pixels, and I have used Python to guess the frequency of each signal by looking at the zero crossings and then averaging them. And then now you have an average time between two zero crossings, and then if you invert that, you can get your frequency. One other trick I would like to show you that I did for this simulation is I have some parameters that I set for Python, for SPICE over here, but I also need to use this in Python. So the way I pass this directly onto Python instead of managing them at two separate locations is I have created a voltage source, and then you set the voltage of this voltage source as the parameter, and in Python I have actually read this parameters in. You can see I'm reading this parameter in, so I don't have to retype them twice. This Python script, so it grabs the electrical signal from each pixel. It also grabs the correct result because it's saved with the schematic, and then it estimates the frequency for each signal, and then calculates the correct time delay. From the time delay, then we can calculate the velocity, and we can also look at the distance between these points. All right, that concludes my presentation for today. Now we're gonna take a few polls and then get some questions.
Okay, the last poll is up. Please take a second to answer. And the final OptiSPICE session is tomorrow at 11 a.m. So Jem will also be running that. It's going to be on advanced applications. So please also attend that if you're available at that time. I've already provided the link in the chat window for the webinar week session listings. Again, you can find quite a bit of info there. You can sign up for additional sessions. You can check on the $50 draw winner, which for this session will be announced at noon Eastern Standard Time today. And you can also get any of the previously recorded webinars. Just click on the link and click the register button with your information, and you'll be taken right to the recording. So with that said, I'll go ahead and pass it back to Jem for any questions.
Okay, so we have one person here asking about the difference between OptiSPICE and OptiSystem. That's actually a really good question. The main difference is the way they run the simulation. In OptiSystem, the old models are run sequentially and separately. So if you're simulating for 20 nanoseconds, each model is going to take an input, simulate for 10 nanoseconds, and then output to the next model. In OptiSPICE, we actually don't do the simulation this way. So at the first time step, we would generate the results. We would put everything in one large matrix, and then solve the equation simultaneously, and then that gives us the time step, the result for the next simulation. So at every time step, all the models are updated, and all the models calculate at the same time. This allows you to do feedback and reflections very naturally, versus in OptiSystem, it can handle feedback and control circuits, but not at the level of OptiSPICE, not with the same ease. So I'll wait a few more seconds for other questions. All right, well, if you have any other questions, you can always email us at our support. We'll be happy to answer them. I think this concludes our presentation for today, and thank you for listening.
Thanks, everybody. Have a good day.